in a very, for the math audience, if you will, or those who know what are groups, let me just start by saying the goal of my talk is to tell you first, it's twofold. First of all, it's to tell you sort of a non-standard model of how mathematics collaboration was done very recently, started very recently. And secondly, so in the first course that you see in college as a math major, in other things, you see what is a group, a ring, a field, a vector space. So I want to tell you a new definition of an abelian group, one without roots of unity, okay, to be very precise. Okay, so without further ado, so let's start from slightly broader. So, the broader sciences have seen many highly collaborative projects. Here are some examples. One, of course, is the Genome Project. As it says below, these data are from some other slides, I guess. There are 200 plus authors on this paper. Some of them actually are institutions. There are many more human beings involved. The Higgs boson, of course, there are apparently 3,000 plus authors on this paper. Gravitational waves, which is very recent. There are at least 100 plus institutions, 800 plus authors. I could see that from the archive version, right? So, there is this standard, there is this tradition, and these are, of course, maybe some of the most famous papers, but in general, there is a tradition in the broader sciences of large scale collaboration. What about me? I come from a field that has lagged behind, and maybe because it's theoretical in nature or for what reason, but it still largely sees, individuals sitting at their desk in seclusion, in isolation, doing research. Maybe the pandemic has really changed the dynamic a little bit, but it's still by and large individuals or 2 people or 4 people, and that's it, right? And not only that, it's so much ingrained in us that it's almost like romanticized in folklore. So some of the early names, Newton, Leibniz did not know what Newton was doing. Of course, there are other reasons for that, but communication was a problem. Fermat was sitting at his desk and wrote, okay, I have a truly beautiful proof of this question, I can't fit in this margin. Galois work was incomprehensible to people even after he died. And then Hardy was sitting at his desk and he got some letter from some clerk in South India working in isolation. Of course, we all know the story of the man who knew infinity. But even later, 30 years ago, in the day of the internet, Andrew Wiles worked secretly to prove Fermat's last theorem. Perelman worked in isolation for these to get $1 million and the Fields Medal, which he both declined. And very recently, Yitang Zhang worked by himself to prove this thing about twin primes or bounded gaps. So the only thing he didn't do alone in isolation was to work at a subway, but the mathematics was all completely in isolation, right? And so, and there are many other examples, of course. So what I want to describe to you today was a modern kind of collaborative mechanism that I was part of, called the Polymath project. Well, so the Polymath project is a bunch of different projects. I was part of one of them, and that helped answer this basic question about groups. So groups are, as I said, the first thing one sees well, we also see it in the broader sciences, but yeah, so we see it in mathematics. So the first thing I saw on day 1 of my college in IISc Calcutta was what is a group, and so the first thing out of school, right? So, but yeah, so groups, so you have the water molecule or the ethane molecule, and you have symmetries of these, rotational reflections. You have, if you take a circle, you see the group of rotations in the plane. So basically, the idea is there is some system, and there are these transformations that preserve the system as a whole, but maybe change things inside this, change the constituents, right? Symmetries, basically. So we all understand groups as maybe objects and elements of groups as symmetries. So we saw something like the shear versus the shuffle, and the shuffle versus the shear. These are all symmetries, as I was told very recently. Okay. There are the Lorentz group of symmetries, but you can even look at vector spaces. So, if you take some, say, eigenspace of some matrix, then sure, that's a set, that's a space. How is it a set of symmetries? Well, you think of each vector as a translation operation on the vector space. So if you translate by something, you still preserve the whole space, you change the vectors in it, right? And so the idea is you are basically permuting the objects of a set on which those symmetries act. And so that's why in mathematics, in fact, the set of permutations is actually called the symmetric group, because it's the group of symmetries or permutations, right? Okay, so now given two systems, given two symmetries of a system, one can do a few things. One can compose two symmetries in some order, alpha composed beta or beta composed alpha, and act on the system. Or you can also reverse the symmetries, right? You can sort of go backwards in time, if you will. Of course, if you take some one symmetry and you have its inverse and you compose them in either order, that does nothing, right? You rotate by 20 degrees and you unrotate by 20 degrees clockwise and counterclockwise, you just get back the original state of the system, so you get the identity symmetry, right? And so a group basically consists of all of these things, right? So I'm just defining this formally. Okay, and then this was this question about, so no, we saw this thing about whether shear first and shuffle next or shuffle first and shear next give you the same system. I'm just going to give a mathematical example. So these are two invertible matrices, which means you can undo the change you do by acting on the plane by two matrices. And for example, these two are invertible, but if you multiply them in different orders, you get different matrices, right? The 1 minus 1 switch positions. A group is said to be abelian if every pair of symmetries or elements of the group satisfy that the order doesn't matter, right? And I didn't put a full stop here, as you see, because I'm going to say something else. So if you have alpha and beta in this way, and I can post multiply, for example, post compose by alpha inverse and undo the change of alpha, and so similarly then beta, and so I can say this equation holds if and only if this holds, right? That first doing alpha, then I read it in reverse order. First doing beta inverse, then alpha inverse, then beta, then alpha gives you the identity symmetry. If that happens for every pair of symmetries, then that means alpha and beta commute for every pair of symmetries, and that means the group is abelian. That's the definition. That's the old definition. I want to give you a new one, right? Okay, so this quantity in red is called the commutator, and basically the commutator is trivial if and only if the elements commute. So this is just basic group theory. Okay, that is one side of the picture, and the other side of the picture, so that's the thing I want to define. This is how I want to define it. So I'm just going to use the norm. Okay, the norm of any vector, if you've seen coordinate geometry in high school, is the length of the distance of that point from 0, right? And it satisfies two or three things. One is that except every other norm has positive value, strictly positive length. And if you add the vector, take a vector twice, thrice, and you take the length of that, that is 3 times the length of the original vector. So just linear scaling. For every positive integer, this is true. So I'm going to isolate these properties and call this a norm on any group. A norm on a group is the same notation function, takes an element of the group of symmetries or takes an element of the group to real numbers. Satisfies that every norm is always positive for non-identity symmetries, right, or non-identity elements, and the identity has norm 0. Then the length, the triangle inequality, the length of one side of the triangle is less than the sum of the other two sides. That's basically saying the same thing here. And this is the property I wrote down here. Here the group operation under translations, right, was the plus. Here I'm just calling it a general group operation. Yeah, so that's what it is. And so what is an example of such a norm on a group? Exactly the one in the picture, right? Take the plane, which you can think of either just as a set of vectors, or if you want to think of them as symmetries, you can think of them as translations. Either way, this has the usual norm, and the group is abelian, as I said last time, right? You can add vectors in either order. You know the usual parallelogram picture, right? And the diagonal is the sum, whether you go this way or that way. The group is abelian. In fact, every abelian, and I need one last ingredient, which is torsion free. Torsion free just means I don't have roots of unity. So the invertible matrices, this is actually a matrix which is not 1, but if you square it, it becomes 1. I don't want that. I don't want roots of unity, because roots of unity are bad in this way, right? If I have an element which is square is 1, then twice the norm of alpha is 0, so alpha should be 0 by dividing by 2, but alpha was not the identity, so how can alpha be 0? So the torsion free is sort of necessary to have a norm in any case. So anyway, so the moment I can avoid roots of unity, basically any abelian group you can prove, one can prove formally using something called Zorn's lemma or the axiom of choice, has a norm. So of course the real numbers have a norm, the rational numbers have a norm, the complex numbers have a norm, R2 has a norm, Rn has a norm, but any abelian group has a norm provided you avoid roots of unity for some obvious reasons. The question that I had, and that's the question I want to answer today, is does there exist a non-abelian group with a norm? A single one, any non-abelian group. So this is one of these stories which, if somebody stumbles around in the dark and discovers penicillin or something like that. I asked a completely harmless question for reasons of my own that came from probability theory with a collaborator, and then from this follow-up, this paper, the preprint was in 2013 or 2014 I think, and then I came to this question later, shortly after, and then I started emailing people, do you know of a non-abelian group with a norm? very basic question, extremely basic to define, high school students can understand it, or maybe college first year. Nobody knew. No examples were known, and no theorem was known that said such a group cannot exist. So what is it? It's either you can find an example or you must show that it doesn't exist. Okay, so then I kept asking people, nothing happened. Eventually I joined IISc and then I went back, I joined IISc and went to UCLA to visit a collaborator. This is a very famous mathematician, he's got the Fields Medal and many other prizes. This year he was the chair of the Fields Medal committee that announced the Fields Medals last week, or this week, sorry, yeah. So here is what we discussed. Suppose take any group with a norm. The question is, does it have to be abelian or can there be a non-abelian group with, take two elements. So do they have to commute or not necessarily, right? The key quantity that we identified, which I will call as KQ, is the norm of the commutator. I told you what the commutator was. So suppose a group has a norm, take two elements, take their commutator. I want to prove that this quantity is 0. Why? If I can prove that this quantity is 0 for every pair of alpha and beta, when is the norm of anything 0? When that element is the identity. When is the commutator the identity? When those elements commute. So if I can prove that this number is 0 for every pair of alpha and beta, then every commutator is trivial because that's the only way the norm can be 0. This is trivial if and only if the group is abelian. So that's the strategy we wanted to use. We still didn't know if this is all true or not. Maybe there is a non-abelian group with a norm. But so anyway, so if you want to prove it, Tao is primarily an analyst, he was trained as one, so of course either you can prove it 0 exactly, like in algebra, we prove exact identities, or you try to do analysis where you have less than epsilon, delta, some errors, bounds, and so that's what he said we should try. So okay, it's easy to prove it's less than 4, modulo the assumption that alpha and beta each have norm less than 1, so you can rescale so that the norms are less than 1. It's easy to show it's less than 2. It's not that bad to show it's less than 4/3, but I want to get to 0. So I want to show that something is less than every positive real number. Only then is it 0. Norms are non-negative, so just show that it's less than every positive real number. That's a property that Archimedes knew, right? It's called the Archimedean property of the real line, or at least it's attributed or named after him thousands of years ago. Can we go down to 0 in some way? I will not tell you the mathematics, I will tell you the story of the Polymath project, right? So I'm not going to give you any proofs, but I can tell you that the proofs are all sort of understandable in sort of, say, the second year of math majors or third year math majors. You can understand the entire proof, and yeah, so the statement itself is so basic. Right? Does a group have a norm, non-abelian group? So it's as basic as that. The proof, so you can't use any Silo theorem or some classification of finite simple groups anyway, they're torsion free, or Lie theory or Lie groups. You just use extremely simple first principle arguments to answer this question, because that's all you can use. Anyway, so the point was I was coming back to India from California, so he asked me, can I put it on my blog? I said, please go ahead. His blog is again very famous, lots of people read it. And so he put this question. He asked it on the free group, but the proof actually works out on any group. Here is a question posed to me by Apoorva that I don't know the answer to. He described the problem. He mentioned 4, 2 and 4/3, these bounds. And then he said, what is not clear to me is if one can keep arguing like this to continually improve that upper bound to the point where it must vanish. The moment the upper bound goes down to 0, the key quantity is 0, the commutator is 0, the elements commute. Anyway, this feels like a problem that might be somewhat receptive to a more crowdsourced attack, and so I am posing it here in case any readers want to try and make progress on it. And so this happened, I boarded my flight. It's a 17-hour flight from San Francisco to Delhi. I get off and I check my internet, and this whole thing has exploded. There's tons and tons of comments, people have been trying approaches. And so that is the next thing that I want to say. It's a non-standard project, especially in mathematics, because first of all, the point 1, it was all done online on his blog. The entire proof, the entire process of discovery, all the comments, new suggestions, new approaches, okay, this doesn't work, now let's do something else, everything was on the blog. And luckily I was jet lagged, so I had an alert for his blog, so every time some new post would come, I would get a ping, and then jet lag helps sometimes. So I could follow the whole process. So this is all in Indian Standard Time. He posed these bounds. As I said, I'm not telling you the proofs, so I will not tell you anything technical. Attempts, the first 2 days were spent in trying to find an example. Okay, maybe there is a non-abelian example. Using all kinds of algebraic topology, geometric group theory, solvable groups, Lamplighter groups, this, that, forget the technical terms. Then people said, fine, it doesn't look like it. So they proved that many things don't work. The process led to lots of negative results. Many things don't work. Then they said, okay, let's try to bring that constant down to 0. So we got to, from 4/3, people got to 5/4, which is an improvement of 1/12. 1 hour later it got to 19/16. It's improvement of 1/16 or something like, yeah, I think so. Anyway, and then, but you see all of these are above 1, so people tried to go below 1. Finally, about 7 hours later, it was successful. So we went below 1. We have to go down to 0, of course, right? So the norm of a commutator is always less equals 1, less equals 22/23. And at this point, the second new or non-standard part of this whole project begins. Human intuition failed. People kept trying, lots of attempts, like hammering away at a wall. And the wall did not break. Okay. And then my colleague here, Siddharth Gadgil, he was busy in simultaneously throughout these 3 days in both sides. He was also trying to find the non-abelian group, and he was also trying to prove the constant is going to 0. So he's remarkably creative, and he proved, he used a computer, he ran a search of about 2 to the 1,000 searches, queries, and finally managed to break through. The computer found an example. So that's the second non-standard part of this. It was all on the blog. And there was a computer that was crucial. When human intuition failed, the computer provided it. So this is the proof that he gave. So first of all, he posted on Tao's blog again. One can get a bound improving from 0.956 to 0.816 with a brutal proof, like just brute force. He just made it search. Then he found, the computer found it, he could recognize it, he could encode and make the computer write it in a way that human beings can read, mathematicians can read. And then he said someone cleverer can extract some inequalities from this. Within 100 minutes, somebody sitting in Utah, all the way across the world, not only said, this is beautiful, so on and so forth, but here are what the first 43 lines established. He decoded the whole thing. The next 30 lines established this, the next 30 lines established this. This is very well done, and here is how to improve on it. And all of this, and then he typed it up, everything in 100 minutes to the dot. So there are some remarkably smart people who are also, are sitting over dinner and reading Tao's blog. And so that's what happened. So Pace Nielsen, so Gadgil, Nielsen, me, Tao, we are all collaborators on that project, of course. So Nielsen improved this one. This is all India time. He was sitting at, this is night in Utah, right? And then 4 hours later, somebody went to 8/11. 4 hours later, somebody went to 2/3. But you see, each of these is not actually getting us close to the answer. We want to get 0. Finite improvements, if you think about it logarithmically, these are all negative numbers in logs. But they are finite negative improvements. We want to get to log of 0, which is minus infinity. So at each step we are making progress, but we are no closer to minus infinity than where we were in the previous step. So we need something more, one more step. And that step was given by my colleague, our colleague in Germany, Tobias Fritz. Sorry, I'll take one more minute. He had this idea of not just looking at the norm of the commutator, but norms of such elements, and then writing some kind of a discrete heat equation down, and then noting that there is a probability involved in this. And then Terence Tao finally, Sir Terence Tao the knight, I guess, dealt the final blow to the dragon. And 3 hours later, the proof was done. And this is the proof. He applied something called a simple random walk and a Chernoff bound, which we later simplified to just the weak law of large numbers and binomial combinatorics. So this project actually connects geometry, algebra, analysis, probability, and combinatorics. And it's really a slogan for the unity of mathematics. Because, yeah, of course, no math talk should not have a theorem. So here is my theorem. Let G be any group. Then G has a norm if and only if G is abelian and torsion free. So for those of you who like algebra, abelian groups, first thing you see. Well, here is an analysis characterization, definition, if and only if, of an algebraic fact. If you like norms, here is the next one. If and only if G is an additive subgroup of a Banach space, or of R2, or of Rn, or of Hilbert space. Take some space, take any additive subgroup with the same norm inherited from the Hilbert space. That's a group. That's a group that has norm. That's a group that's abelian torsion free, and there are no others. And this is the paper, and I guess I should stop here. Thank you. So I should say that, right? That's a fair point. So this is you see, the paper is authored by something called DHJ Polymath. Individual names are not mentioned. Then there's a separate Wikipedia page where the steps of discovery and the individual contributors are mentioned, like our names, our grants, our funding agencies. But the paper is by Polymath. So the idea is, this is the philosophy is what is agreed to be as the author.
I remember another famous example, where I admire mathematicians. Normally they work alone. They are non-communicative. when this Fermat's last theorem was proved by Andrew Wiles,
Yes.
apparently there was gaps and holes.
That's right.
So the entire community worked together.
Yes.
And it took an year or so to fill it up. So
That's
that's
right.
very admirable.
Yes.
Very rarely it happens in other communities.
And we still, we try, So this is of course a very new idea that Timothy Gowers introduced, I think, about 10, 15 years ago. But this does encapsulate the philosophy that was going on earlier also. Yes, Vijay. Yes. Sorry.
So I'm just wondering, so for example, are there thoughts on how to use these sort of ideas to think of other kind of things? Like, can you try to characterize simple groups without normal subgroups? Or
So finite simple groups have been classified in this huge program, Polymath-like, but not
but
Polymath.
in this analysis way.
Ah,
So can you find a condition by which group is
that is
simple
a very
by-
nice question. I have absolutely not thought about this, but yes. The connections are just, this is itself just a few years old, and it's starting to slowly get cited and explored, but maybe this thing I should let me email Tao, I should say. Sorry? Put it in his blog, exactly. So actually the week after this was solved, he immediately started a new Polymath project on the Riemann hypothesis, that the De Bruijn-Newman constant to improve that. So he is a very busy person, but I should at least email him and ask him to check if it's, what does he think, he should ask around, and it's a nice question. Can this characterization of abelian torsion free groups be applied to other things? Yes, and with this same analysis philosophy. Absolutely right.